Welcome everyone. Today we're going to explore Module 3, which focuses on industrial manufacturing technology. Specifically, we'll be diving into sheet metal and forming processes. This is part of the PBAUT 404 course for Semester 4. Over the course of this presentation, we'll cover the fundamental techniques and applications involved in sheet metal forming. I'm excited to guide you through these concepts and share some valuable insights. Let's get started. Let's take a closer look at the knowledge level for this module. We're working at K2, which means we're focusing on foundational understanding. In terms of contact hours, we've allocated 7 hours to cover this content thoroughly. Now, what's included in this coverage? We'll explore sheet metal operations, which are essential for shaping and forming metal sheets. We'll also delve into rolling mill theory, giving you insights into how metals are rolled into different thicknesses. Additionally, we'll look at drawing processes, both for wire and tube manufacturing, highlighting how metals are pulled into specific shapes. We'll examine extrusion characteristics, understanding how metals are forced through dies to create various profiles. And finally, we'll go over forging principles, which are crucial for understanding how metals are shaped under compressive forces. This module is part of the overall syllabus, specifically Module 3, and it ties into the broader theme of metal forming and manufacturing techniques. All of these topics are interconnected, helping us build a comprehensive understanding of how metals are processed in different industrial applications. Let's take a closer look at sheet metal forming, particularly some of the complex operations involved. These include processes like stretching, flanging, and hemming, which are commonly used in automotive body panels. These techniques rely on applying force to the sheet metal to change its shape, rather than removing any material. So, the focus here is on modifying the geometry of the metal to achieve the desired form. A key parameter in this process is the bend allowance, or BA. This measurement is crucial because it helps ensure that the final length of the sheet after bending matches what we need for accurate assembly. Essentially, it accounts for the material that stretches or compresses during the bend, helping us maintain precision. Now, when we talk about bending mechanics, we're referring to how the sheet metal strains around a straight axis. The inside of the bend experiences compression, meaning the metal gets squeezed together, while the outside is stretched, which causes elongation. Understanding this strain distribution is vital for predicting how the metal will behave during forming. Connecting this to our overall theme, mastering these bending and forming techniques is essential for producing complex, high-quality automotive panels efficiently. It allows us to shape metal precisely while maintaining its structural integrity. Let's take a closer look at the maximum draft calculation. Here, mu represents the coefficient of friction, which plays a crucial role in the rolling process. R is the roll radius, and together these factors influence how much material we can deform in a single pass. Now, when we talk about mill types, there are several common configurations. These include 2 high mills, where 2 rolls are used, 3 high mills, which incorporate an additional roll for more versatility, 4 high mills that feature backup rolls to support the work rolls, cluster mills, which are designed for very heavy reductions, and tandem mills used for high-volume, continuous processing. In the rolling process itself, material is pulled into the gap between 2 counter-rotating rolls. This friction between the rolls and the material is what actually pulls the material through. As the material moves through the gap, its thickness reduces, but at the same time, its length increases. This entire process is governed by the mechanics of rolling, which we'll explore further under the theory of rolling. The key idea here is that the friction and roll radius directly influence the maximum amount of deformation, or draft, that we can achieve in a single pass. Understanding these concepts helps us optimize the rolling process to achieve the desired material properties and dimensions efficiently. Now, let's look at forming flat sheets into cup-shaped parts. The key factor here is the ratio of the diameter to the depth of the part. This ratio actually determines how complex the process will be. If you have a shallow cup with a large diameter, it's generally easier to form. But as the depth increases relative to the diameter, the process becomes more challenging because of material thinning and potential wrinkling. Moving on to deep drawing, this process is quite similar to wire drawing, but with an added twist. Instead of just pulling material through a die, we use a mandrel inside the part to help maintain the internal diameter and wall thickness. This ensures the final shape is precise and uniform, which is especially important for components that need to fit perfectly or have specific structural requirements. Next, we have tube drawing. This involves pulling a metal tube through a die to reduce its diameter. It's a critical process for manufacturing electrical wires and cables because it allows us to produce long, thin, uniform wires efficiently. The process improves the mechanical properties and surface finish of the wire, making it suitable for high-quality electrical applications. Finally, wire drawing itself is all about pulling metal through a die to reduce its diameter. It's a fundamental operation in producing wires of various sizes and types. The key here is controlling the process parameters to ensure the wire maintains its strength and surface quality throughout the drawing process. All these drawing operations are essential in shaping metal efficiently, each suited to different final products and specifications. They highlight how versatile and precise metal forming can be when we understand and control the process parameters. Now let's look at some of the key applications of high-precision forming. You'll find it in currency production, where it helps create coins with detailed and consistent designs. It's also used in making metals, which require fine detail and durability. Moving to everyday items, kitchenware often benefits from these processes, ensuring both quality and precision. And in aerospace, where safety and exact specifications are critical, high-precision forming plays a vital role in manufacturing components. Next, I want to highlight two important techniques within this field: metal spinning and coining. Metal spinning involves forming a rotating disc into hollow parts by using a mandrel, which helps shape the materials smoothly. Depending on the material thickness, this can be done as hot spinning, where the metal is heated to make it more malleable, or cold spinning, which is done at room temperature for more precision. Then there's coining, a type of closed die forging process. It's really about creating fine details and achieving high accuracy, making it perfect for applications requiring intricate designs. One key point is that no flash, those excess bits of material, are allowed in coining, which ensures a clean, precise finish every time. All of these methods, spinning and coining, are essential tools in high-precision forming, helping us produce high-quality, detailed components across various industries, from currency to aerospace. Now let's take a closer look at different types of metal extrusion processes. First, there's indirect extrusion, where the die moves toward the billet, effectively pushing the metal through the die from behind. Then, we have direct extrusion, where both the ram and the billet move in the same direction, with the ram forcing the metal through the die. These methods are commonly used to produce things like aluminum window frames, tubing, and structural profiles. The key idea here is that metal is forced through a die to create long products that have a uniform cross-section along their length. This process allows us to produce complex shapes that would be difficult or impossible to achieve with other methods like rolling. It's also important to understand some process characteristics, such as how extrusion is a versatile way to form metal into various profiles, maintaining shape consistency and enabling the production of intricate designs. This makes metal extrusion a crucial technique in manufacturing, especially when precision and complex cross-sectional shapes are needed. When it comes to tooling, forging relies on heavy-duty dies and hammers, or sometimes hydraulic presses, to deliver powerful energy into the metal. This force shapes the material precisely where we want it. Temperature control is also crucial. We usually perform forging at high temperatures, which makes the metal more ductile. This reduces the amount of force needed and allows for a smoother shaping process. An important aspect of forging is how it affects the grain structure of the metal. By aligning the grains with the shape of the part, we significantly boost the strength of the final product compared to casting. This grain alignment results in forged parts having superior fatigue resistance and toughness. That's why we often see forging used for critical components like engine crankshafts and landing gears, where strength and durability are essential. Overall, the principles of forging offer clear industrial benefits: stronger, more reliable parts that perform better under stress, which ultimately improves the safety and efficiency of the machinery we rely on. Let's take a closer look at drop forging. This process involves shaping metal by dropping a hammer or a die onto the workpiece. It can be done in different ways, primarily categorized into closed die and open die forging. In closed die forging, the metal is poured into a die that completely encloses it, shaping it precisely to the die's cavity. This method is ideal for producing complex, high-strength components with tight tolerances. Open die forging, on the other hand, involves deforming the metal between two dies that do not completely enclose the workpiece. This gives more flexibility and is often used for larger, simpler shapes. An important aspect to note is roll forging, which falls under these classifications. It's used specifically to reduce the thickness of bars while increasing their length, which is essential in manufacturing elongated parts. Overall, these forging classifications help us understand the different techniques available to achieve various shapes and properties in metalworking, depending on the desired outcome. Now, let's take a closer look at the differences between hot working and cold working. When it comes to temperature, hot working is performed above the recrystallization temperature of the material, which allows the metal to deform more easily. Cold working, on the other hand, happens below that temperature, making the process more challenging, but often resulting in different material properties. In terms of surface finish, hot working typically produces a poor surface finish, often with oxidation or scale forming during the process. Conversely, cold working results in an excellent, shiny, and smooth surface finish because the deformation occurs at lower temperatures, minimizing surface oxidation. When we consider strength, hot working tends to produce a uniform and refined grain structure, which can be beneficial for certain applications. Cold working, however, leads to higher strength due to work hardening. Basically, the metal becomes stronger as it's deformed at lower temperatures. Finally, regarding power requirements, hot working generally requires less force and energy because the metal is easier to deform at high temperatures. Cold working needs more power since the material resists deformation more strongly at lower temperatures. So, in summary, hot and cold working each have their unique advantages and challenges that influence their suitability for different manufacturing needs. Let's take a closer look at the typical flow stress behavior during cold forming, which is beautifully illustrated here. As you can see, the curve demonstrates how the material's stress responds as it undergoes deformation. Initially, you'll notice that the stress increases rapidly with strain, which is a characteristic of work hardening. This is where the material's internal structure is strengthening as dislocations multiply and interact. As deformation continues, the flow stress tends to level off or sometimes even decrease slightly, indicating a balance between work hardening and other factors like strain rate or temperature effects. This behavior is critical because it influences how we design forming processes. Knowing how the material strengthens helps us predict the force needed at each stage. Overall, understanding this flow stress trend helps us optimize the cold forming process, ensuring we apply just the right amount of force to achieve the desired shape without causing defects or unnecessary strain. It's a key piece of the puzzle in controlling material behavior during manufacturing. Let's look ahead to our next module, which will focus on advanced machining processes. This will take our understanding of manufacturing to the next level by exploring more complex and precise techniques. I also suggest a couple of project ideas you might find interesting, such as analyzing deep drawing or forging processes, which are both critical in shaping metal components efficiently and with high quality. Now, we've covered a lot about sheet metal and forming in this module, and I want to open the floor for any questions you might have. Feel free to ask about anything we've discussed or clarify any concepts. This is a great opportunity to ensure you're comfortable with these fundamental ideas before moving on to more advanced topics. Now let's take a closer look at the sources behind these images and what they illustrate about the forging process. First, we have a hammer forging image from Ringrolling Machine, COM, which highlights the traditional method of shaping metal using a hammer or ram. This technique is fundamental in forging, where force is applied to deform the metal into the desired shape. Next, from Xdirectory, COM, there's an image of a forging ram, which is a vital component in open die forging processes. The ram strikes the workpiece to shape it, and understanding its design helps us appreciate the mechanics behind large-scale forging operations. Moving on from Victor Macha, COM, we see a picture of hot die forging, showcasing the use of heated dies to shape metal more precisely and efficiently. This method allows for complex geometries and improved material properties. Then, from YouTube, there's an image related to coin making, emphasizing the importance of forging techniques in jewelry and small-scale manufacturing, where precision and detail are critical. Next, from Lisyang Jewelry, COM, we observe a process of making holes in coins, which demonstrates the importance of forging and machining in jewelry creation, adding functional and decorative elements. From Hanum, COM, we have a diagram of a rolling mill design, illustrating how rolling mills are used to produce metal sheets or strips, contributing to various manufacturing applications. Finally, the images collectively underscore how forging is a versatile and essential process across different industries, from large industrial components to intricate jewelry, highlighting the importance of understanding various forging techniques and machinery.